Welcome back, ladies and gents. We are looking at today the concept of acceleration. There's linear acceleration, so acceleration in a straight line, and angular acceleration, which is the rotation acceleration around an axis. We'll get into those in a second. I also want to have a look at using data to calculate acceleration. So what is acceleration? Here is a basic example of it. We have Usain Bolt on the left of screen. He has a velocity or a speed of 0 meters a second. He's not moving. He is stationary. 7 seconds later, his velocity is now 10 meters a second. So we can conclude from that he has accelerated. He has got faster from 0 to 10. Within 7 seconds, he has accelerated. So it refers to a change in velocity in a given time frame. Okay, so the time frame in this instance, again, is 7 seconds. And you can see clearly there has been a change. So it's about looking at that change in velocity or change in speed. It's measured in meters per second squared. So there's a few terms that you need to be aware of and be able to use. Acceleration, which is obviously an increase in velocity over a period of time. And that's going to result in a decrease in the amount of time taken to travel that distance. So that's where they can trick you up sometimes, is they'll ask you if someone's acceleration, but their times are getting bigger. If their times are getting bigger, it's taking them longer, so they're actually slowing down. Okay, so acceleration will always have a positive value once you calculate that. Deceleration, same as increase and decrease. Whenever you see D on the front of a regular word, then usually it's the opposite. So in this case, deceleration is a decrease in velocity or speed and an increase in the time taken. So it will have a larger time because it's decreasing. Okay, so a acceleration will have a negative value. So if someone has slowed down, their acceleration value that you might come up with will be negative 1.5. So that means they have slowed down by 1.5 meters per second squared. And lastly, but not leastly, there's the concept of constant speed or no acceleration. So when you're not getting faster or slower, you're staying at a steady pace. So we call that a constant speed. It can also be referred to as no acceleration. Okay, and a constant speed will always have a value of 0. Don't confuse that with being stationary, and more on that in a second. So here are some examples in sport. Marathon runner increasing their velocity in a sprint to the finish line. So they've been going at a steady pace for the duration of their marathon, and then they were involved in a sprint at the end, which will cause them to increase their velocity. And because they have increased their velocity, they have accelerated. A ball accelerates when released from a bowler's hand in cricket. As the bowler is running in, the ball is also moving in with him. And as they swing around their arm, it would accelerate, but it would accelerate even more when it's released with all that force from his hand to the wicket. So that has undergone acceleration. Deceleration in sport, a cyclist that hits the brakes to avoid crashing. And that's a clear example. They're going fast or faster. They hit the brakes very suddenly. That is decelerating. Even if it wasn't suddenly, even if they slowly hit the brakes, they are still decreasing in speed or velocity. So they are decelerating. And a constant speed, 100-meter sprinter maintaining a steady speed for the last 50 meters of a race is an example of a constant speed. So there's a formula to calculate acceleration. And sometimes they put VF and VI for the final velocity is VF and VI is the initial velocity. But all you need to remember is the 2 points that you're trying to work out whether they've accelerated, the final point minus the initial point, the speeds of those two, divided by the time taken. So we're going to do an example in just a second, but the velocity is usually measured, all these measurements, unless the question has asked for something else. So if the question doesn't stipulate kilometers or milliseconds, then you can assume that the velocity is in meters per second, that the time taken is in seconds, and you can assume the acceleration will be in meters per second squared. Okay, so it's important that you don't forget to put those unit of measurements in, especially for acceleration if you're asked to calculate it. So going back to this, let's calculate Usain Bolt's acceleration during this time. We have all the figures needed. We have his final velocity, which is 10 meters a second. We have his initial velocity, which is the velocity of his starting point, which in this case is 0 meters a second. He was not moving. And we have the time taken. The time taken was 7 seconds. So this should be pretty simple. It's just about putting the right values and working them out in the right order. So again, the initial was 0. The final was 10, so 10 minus 0 will give us a figure of 10, and the time taken was 7 seconds, so 10 divided by 7 gives us an acceleration of 1.43 meters per second squared when rounded off to 2 decimal places. So, just to sum up what we've gone through so far, that is the easiest way of remembering the acceleration time formula. But don't get too caught up by the letters. It is simply the final minus the initial divided by the time taken. So acceleration is the change in velocity within a given time. It can be positive, which is speeding up, or negative, slowing down or decelerating. It's measured in meters per second squared, and a body moving at a constant speed will always have an acceleration of 0. So it's important to stipulate this doesn't mean they've stopped. Just because their acceleration is 0 does not mean their speed is 0. It simply means their speed has not changed. So they're moving at a constant speed. So looking at angular acceleration, it's the same as linear acceleration. The only difference being we're now talking about rotational distance. So we're looking at degrees rather than meters. All right, but it's still per second, so degrees per second. Other than this, it's completely the same concept. So we're going to show you an example of that. So again, there's the same equation. We are just looking at the change in angular velocity rather than linear velocity divided by time. Another way to word this is the final velocity, which will be a degree measurement of how far they have rotated. So it might be 360 degrees, for example, minus the initial. So whatever they started at, it might have started at 0. Okay, divided by the time taken to get from point A to point B. Okay, so let's have a look at an example. A gymnast rotating around a high bar who speeds up from 100 degrees to 300 degrees in 0.5 seconds has an annual acceleration of 400 degrees per second. So that's the answer. How did they get that answer though? All right, well, they use this equation. We have final velocity minus initial. So the final, okay, was 300 degrees. That's the speed in which they got to. The starting speed was 100. So 300 minus 100, and that will tell us our change in angular velocity. So 200 degrees is our change in angular velocity. The time is 0.5 seconds. Okay, so very simply, 200 divided by 0.5 will give us 400 degrees per second squared. All right, let's have a look at just some more general acceleration, not so much angular acceleration here. I want you to think about a 100 meter sprinter. If we break up the 100 meters into 10 meter splits, would they experience the most acceleration in the first 10 meters? Why? Pause, have a think about that, and press play when you think you're ready and you have an answer. Okay, now for the second part of this question. Now let's say between splits 4 and 5, their acceleration is 0 meters a second. Does that mean the run has stopped? Has the person stopped between splits 4 and 5? Again, pause. So very simply, yes, the highest acceleration would be in the first 10 meters because they're going from 0. They're starting from 0. Every other 10-meter split after that, they already have a positive speed figure. So the biggest jump is going to be when they're going from stationary to when they're moving. Okay, so yes, it would be the biggest split. Have they stopped because their acceleration is 0? No, they have not stopped. It's just that their speed is the same. So there is no acceleration, but that does not mean there's no movement. It just means they're moving at a constant speed. So, well, there you go. The answer's already there for that one. But what is acceleration? It is a change in velocity in a given period of time. And there's an example here, which is similar to the one I gave you before. All right, I want you to look at graphs. Sometimes they ask you to look at a graph in order to be able to calculate someone's acceleration. So I just want to take this through with you. Firstly, just have a look at what this graph is telling us. We have the 0 time frame, and then we have this is where they finish the race. So in this case, they finished the race in roughly 9 points. Well, there it says 9.83. That is the time, and this is the speed. So you can see they started the race and very quickly went from 0 to say 6 meters a second. All right, and even quicker did they get to 10 meters a second, and then they start to move out here. Then we have this flat part up here. So if I was to ask you to look at this person's acceleration, what would you say has happened between, say, 6 seconds and 8 seconds? Pause the video. So they're still moving, as you can see, because their meters per second is over 12, so it's quite high. And that means they are definitely moving, but their acceleration would be 0. They're not increasing, they're not going higher in this meters a second speed indicator, and they're not going lower, they're not decelerating like they are this last part here. So it's a flat line, which tells us that they are not accelerating, not decelerating, but moving at a constant speed. So how can we calculate acceleration just from using this? So we just take two figures that we want to find out the acceleration between those two figures. So this has given you the example. Usain with an average speed of 5.38 in a time of 0.91 seconds and 9.83 at a time of 2.35 seconds. So there's two different split times. We can then calculate this acceleration. All right, so 9.83 is his end velocity, his final velocity, and the initial or the average speed is 5.38. So if we want to work out those, it's simply minus them, and that gives us the acceleration. And once we have the change, it's simply a matter of working out the time difference between those two values. So you can see at a time of 0.91 seconds, that was his initial time, and the final time of 2.35. So similar, to work out the difference between those times, I should just subtract the starting time from the ending time. So 2.35 minus 0.91. Okay, and that will give me 1.41, and then 4.45 divided by 1.41 gives me the answer and the acceleration of 3.16 meters a second. So, can you do this? I wonder. We've just been through a similar question. Label the three sections of the graph to demonstrate whether they are positive, negative acceleration, or have no acceleration. Pause and do that now. So there you can see the answers. Hopefully that was pretty straightforward for you. All right, a ball moving with a constant velocity will have, put your answer down now. Correct answer is, of course, no acceleration. It's moving at a constant velocity. It's not speeding up, it's not slowing down, it's constant. Two sporting examples where negative acceleration or deceleration of a body or an object occurs. So, a rugby player slowing down when bumped by an opponent, the bowl slowing down to stop next to the jack in lawn bowls. So, as the person releases a lawn bowl, it's going to be traveling much faster than it is before it stops and when it stops. So, over that period of time, it is decelerating. And an AFL footballer running towards the ball has to slow down to pick up the ball off the ground. He might only slow down, he might be highly skilled, highly agile, he might only slow down a tiny little bit. Any negative change in velocity is deceleration. So I would be very surprised if there's an AFL footballer who could scoop a ball off the ground without having to slow down the slightest little bit. All right, now I'd like you to have a go at these last couple of questions and use the graph from the previous page in order to do so. Thanks for watching.